What preceded our universe? We stand at the threshold of revolutionary discoveries that may finally illuminate the darkness before the dawn of everything we know. For most of human history, the question of cosmic origins belonged to the realm of mythology and philosophy. Ancient civilizations crafted elaborate creation stories, the cosmic egg of Chinese mythology, the primordial waters of Mesopotamian legend, the eternal cycles of Hindu cosmology. These narratives served to satisfy our deep-seated need to understand beginnings, but they offered no testable predictions about the universe we inhabit. The transformation began in the early 20th century. Albert Einstein's theory of general relativity, published in 1915, provided the mathematical framework that would revolutionize our understanding of space and time. Einstein's equations described a dynamic universe, one that could expand or contract, bend and warp. Initially, even Einstein himself was uncomfortable with these implications, introducing his famous cosmological constant to maintain a static universe. But evidence would not be denied. In 1929, Edwin Hubble's observations at the Mount Wilson Observatory revealed that distant galaxies were receding from us, with more distant galaxies moving away faster. The universe was expanding. If we could run the cosmic film backward, we would see everything converging to a single point, a moment of ultimate compression and infinite density that physicists would later term the Big Bang. The Big Bang theory, refined over decades of observation and theoretical work, provides a remarkably successful description of cosmic evolution. We can trace the universe's history from fractions of a second after its birth through the formation of the first atoms, the ignition of the first stars, and the assembly of galaxies and galaxy clusters. We have detected the cosmic microwave background radiation, the afterglow of the Big Bang itself, and measured its properties with exquisite precision. Yet for all its successes, the Big Bang theory confronts us with a fundamental barrier. At the moment of the Big Bang itself, time zero, our physics breaks down completely. The density and temperature become infinite, a mathematical singularity where the laws of physics, as we know them, cease to apply. We cannot peer beyond this cosmic horizon using conventional methods. The Big Bang theory tells us what happened after, but it remains silent about what came before. This limitation has profound implications. If the Big Bang marks the beginning of time itself, then asking what came before is like asking what lies north of the North Pole, a meaningless question. But many physicists suspect this conclusion is premature. The breakdown of our theories at the Big Bang singularity may indicate not the absence of a before, but rather the inadequacy of our current understanding. The search for what preceded our universe began with attempts to solve puzzles within the Big Bang model itself. In the early 1980s, physicists recognized several troubling problems with the standard Big Bang scenario. Why was the cosmic microwave background radiation so uniform across the sky, when regions separated by vast distances could never have been in thermal contact? Why was the geometry of space so remarkably flat, balanced on a knife's edge between eternal expansion and eventual collapse? And why don't we observe the exotic relics, magnetic monopoles, and other exotic particles that many theories predicted should have been produced in the early universe? The solution came from Alan Guth, a young particle physicist working at Stanford University. In 1981, Guth proposed that the very early universe underwent a period of exponential expansion called cosmic inflation. During this brief epoch, lasting perhaps 10 to 1032 seconds after the Big Bang, space expanded by an enormous factor, possibly 1026 or more. Inflation elegantly solved the problems of the Big Bang model. The uniformity of the cosmic microwave background could be explained if the entire observable universe expanded from a tiny, causally connected region. The flatness of space was a natural consequence of inflation, just as the curved surface of a balloon appears flat when expanded to enormous size. and the exotic relics were diluted to undetectable levels by the vast expansion. But inflation did more than solve existing problems, it made new predictions. The quantum fluctuations present during inflation would be stretched to cosmic scales, creating tiny variations in density that would later grow into the galaxies and galaxy clusters we observe today. When the Cosmic Background Explorer satellite detected these fluctuations in 1992, it provided stunning confirmation of the inflationary paradigm. Yet inflation, revolutionary as it was, only pushed the mystery back one step further. What caused inflation to begin, what determined its properties, and most intriguingly, what happened before inflation started. The inflationary epoch represents a bridge between the unknowable singularity of the Big Bang and the well-understood era of cosmic evolution that followed. But bridges, by their very nature, connect two shores. If inflation is our bridge to the observable universe, what lies on the far shore, in the pre-inflationary era that may have given birth to inflation itself? As physicists refined the theory of inflation throughout the 1980s and 1990s, they made a startling discovery. In most realistic models of inflation, the process doesn't end everywhere at once. While inflation stops in some regions, allowing them to become universes like our own, it continues in other regions, spawning new inflationary zones that eventually become other universes. This concept, known as eternal inflation, suggests that our universe is just one bubble in an infinite cosmic foam. The process of inflation, once started, becomes self-perpetuating. Andre Linde, one of the pioneers of inflationary cosmology, describes this scenario as a fractal multiverse, an endlessly branching structure where new universes are constantly being born. Each pocket universe may have different physical properties, different values for the fundamental constants, different numbers of spatial dimensions. The universe we inhabit, with its particular laws of physics and its life-friendly properties, represents just one possibility among an infinite array of alternatives. If eternal inflation is correct, then asking what came before our universe becomes a more nuanced question. Our particular pocket universe had a beginning, the moment when inflation ended in our region and the hot, dense state we call the Big Bang commenced. But the larger inflationary multiverse may be eternal, with no beginning or end in time. This perspective fundamentally changes our view of cosmic origins. Rather than a single, unique moment of creation, we face an eternal, ever-expanding ensemble of universes. The multiverse concept, while intellectually compelling, raises profound questions about the nature of scientific explanation. If our universe is just one among infinite possibilities, how can we make sense of its particular properties? Why do the laws of physics take the form they do? Some physicists argue that we observe these particular laws simply because they allow for the existence of observers like ourselves, a controversial idea known as the anthropic principle. Not all physicists accept the multiverse implications of eternal inflation. Some have proposed alternative scenarios that avoid the need for infinite universes while still addressing the pre-Big Bang question. One of the most intriguing alternatives is the cyclic universe model, which suggests that our universe undergoes endless cycles of expansion and contraction. In this scenario, the universe expands for billions of years, eventually entering a phase of accelerated expansion driven by dark energy. As the universe becomes increasingly empty and cold, it transitions into a contracting phase, culminating in a big crunch that triggers the next Big Bang. The modern cyclic model, developed by Paul Steinhardt of Princeton University and Neil Tirok of Cambridge University, proposes that the Big Bang was not the beginning of time, but rather the latest in an infinite series of cosmic rebirths. A particularly elegant version of the cyclic model is the ekpyrotic scenario, inspired by string theory's extra dimensions. In this model, our universe exists on a four-dimensional membrane, or brane, floating in a higher dimensional space. The Big Bang occurs when our brane collides with another brane, releasing the energy that becomes the matter and radiation of our universe. The cyclic model solves many of the same problems as inflation, but through a completely different mechanism. The ekpyrotic model makes specific predictions about the gravitational waves that should have been produced during the Big Bang. Unlike inflation, which predicts a significant background of primordial gravitational waves, the ekpyrotic scenario predicts that these waves should be undetectably weak. Future gravitational wave observatories may be able to distinguish between these competing scenarios. If the cyclic model is correct, then asking what came before our universe has a clear answer: the previous cycle. To truly understand what might have preceded our universe, we must venture into the realm where Einstein's general relativity meets quantum mechanics, a theoretical landscape fraught with paradoxes and possibilities. At the scales and energies present in the first instant after the Big Bang, quantum effects become as important as gravitational ones, requiring a theory of quantum gravity that we do not yet possess. The period from time 0 to 1043 seconds after the Big Bang is known as the Planck epoch. Several approaches to quantum gravity offer tantalizing glimpses of what physics might look like in the Planck epoch. String theory, which treats fundamental particles as vibrating strings rather than point particles, requires the existence of extra spatial dimensions beyond the three we experience. These extra dimensions might have been large during the Planck epoch, only later compactifying to microscopic scales. In some string theory scenarios, our Big Bang represents the collision of higher dimensional branes. Loop quantum gravity, an alternative approach to quantum gravity, suggests that spacetime itself has a discrete quantum structure at the Planck scale. In this framework, the Big Bang singularity is replaced by a quantum bounce, a moment when a previously contracting universe reaches a minimum size and begins to expand. The universe that preceded the bounce might have been vastly different from our own, perhaps with opposite chirality or different dimensional structure. One of the most revolutionary ideas to emerge from theoretical physics in recent decades is the holographic principle, the notion that all the information contained in a volume of space can be encoded on its boundary. This principle, inspired by the physics of black holes, suggests that what we experience as three-dimensional reality might actually be a projection from information stored on a two-dimensional surface. The Big Bang might represent the moment when spacetime crystallized out of a pregeometric quantum state. The AD-SCFT correspondence, a mathematical relationship discovered in string theory, provides a concrete example of how this might work. This correspondence shows that a theory of gravity in a higher dimensional anti-de Sitter space is exactly equivalent to a theory without gravity on the boundary of that space. If our universe is holographic in this sense, then its entire history, including what we call the Big Bang, might be encoded in quantum information processing on a distant boundary. Some physicists speculate that consciousness itself might play a role in the emergence of spacetime from quantum information. If observation is required to collapse quantum superpositions into definite states, then the existence of observers might be necessary for the crystallization of classical spacetime from quantum possibilities. This view suggests a deep connection between mind and cosmos that echoes ancient philosophical traditions while remaining grounded in modern physics. Black holes, those gravitational monsters that warp spacetime to its breaking point, may hold crucial clues about what preceded our universe. Stephen Hawking's discovery that black holes emit radiation revolutionized our understanding of these objects and revealed deep connections between gravity, thermodynamics, and quantum mechanics. The information paradox that Hawking identified strikes at the heart of our understanding of physical reality. When matter falls into a black hole, its information appears to be lost forever. One intriguing possibility is that black holes are not endpoints of gravitational collapse, but rather doorways to new regions of spacetime. In this view, The matter that falls into a black hole doesn't disappear, but instead emerges as a Big Bang in a new universe. Our own Big Bang might have been the birth cry of matter emerging from a black hole in a parent universe. Lee Smolin has proposed a cosmological natural selection scenario based on this idea. If universes are born from black holes, and if the physical constants in the daughter universe are slightly modified versions of those in the parent, then a process analogous to biological evolution might operate on cosmic scales. Universes that produce many black holes, and thus many offspring, would become more common over time. This scenario offers a potential explanation for the apparent fine-tuning of physical constants in our universe. At the quantum level, particles can tunnel through energy barriers that would be insurmountable in classical physics. An electron can appear on the other side of a wall without ever passing through it, and radioactive nuclei can decay by tunneling through the energy barriers that bind them together. Could the entire universe have tunneled into existence from nothing? This remarkable possibility was first explored by Alexander Vilenkin of Tufts University and others in the 1980s. In quantum mechanics, even empty space, the vacuum, is filled with quantum fluctuations, virtual particles that briefly pop into existence before annihilating each other. Vilenkin showed that these fluctuations could, in principle, give rise to an entire universe through quantum tunneling. The quantum creation scenario suggests that our universe tunneled into existence from a state of nothing, not empty space, but rather the absence of space, time, matter, and energy altogether. James Hartle and Stephen Hawking proposed a related but distinct scenario known as the no-boundary proposal. Using a mathematical technique that treats time as if it were a spatial dimension, they showed that the universe could be finite in extent, but without boundaries or edges. In this view, asking what came before the Big Bang is like asking what lies south of the South Pole. The question assumes a boundary that doesn't exist. String theory, the most ambitious attempt to unify all the forces of nature, has revealed a landscape of possibilities that stretches the imagination. Rather than predicting a unique set of physical laws, string theory appears to allow for an enormous number of different vacuum states, perhaps 10,500 or more, each corresponding to a different possible universe with different physical properties. The Hartle-Hawking proposal suggests that the universe emerged from a quantum superposition of all possible geometries. This landscape of string theory vacua presents both an opportunity and a challenge for understanding cosmic origins. On one hand, it suggests that our universe is just one point in a vast space of possibilities, chosen perhaps by random quantum tunneling events or by the requirements of observer selection. On the other hand, it raises the question of whether string theory can make any definite predictions if almost anything is possible. The anthropic principle offers one way to navigate this landscape. Leonard Susskind, one of the founders of string theory, has argued that the anthropic principle represents a new kind of scientific explanation, one based on environmental selection rather than fundamental law. Just as Darwin explained the apparent design of living organisms through natural selection without invoking a designer, the anthropic principle might explain the apparent fine-tuning of physical constants without requiring a cosmic designer. Critics argue that anthropic explanations are too weak to count as genuine scientific predictions. A radically different perspective on cosmic origins emerges from the intersection of physics and computer science. Digital physics proposes that the universe is not continuous but discrete, made up of finite, indivisible units of space, time, and information. In this view, reality itself might be a vast computation, processing information according to fundamental algorithms that we perceive as the laws of physics. If the universe is computational in nature, then its origin might be understood in terms of information processing rather than energy and matter. The Big Bang could represent the moment when a cosmic computer was switched on, beginning to execute the program that generates our reality. What preceded the Big Bang would then be the preparation phase, the loading of initial conditions, and the setup of computational parameters. Stephen Wolfram has proposed that the universe operates like a cellular automaton. If reality is computational, then questions about cosmic origins become questions about the source and nature of the cosmic computation. Who or what programmed the universe? What hardware runs the cosmic software? Some speculate that our universe might be a simulation running on computers in a higher-level reality, a cosmic version of the virtual worlds we create in our own computers. This computational view of reality suggests that what we call physical laws are actually computational rules. The role of consciousness in physics remains one of the deepest mysteries in science. Quantum mechanics seems to require the involvement of observers to collapse wave functions and determine definite outcomes, leading some physicists to speculate that consciousness plays a fundamental role in the structure of reality itself. If consciousness is indeed fundamental rather than emergent, then questions about cosmic origins become intertwined with questions about the origin of mind. The participatory universe model, championed by physicist John Wheeler, proposes that observers don't just passively witness reality, but actively participate in its creation. In Wheeler's famous thought experiment, the observation of a distant quasar today might retroactively determine whether a photon took one path or another around an intervening galaxy billions of years ago. If observers can influence the past through present observations, then the existence of conscious beings today might have played a role in determining the initial conditions of the universe. Some physicists have proposed that consciousness itself might have preceded the physical universe. In this view, mind is the fundamental reality, and what we call the physical universe is a particular pattern of experience within a cosmic consciousness. The Big Bang would then represent not the beginning of reality, but the beginning of a particular dream within the cosmic mind. These ideas remain highly speculative and controversial within the physics community. While the pre-Big Bang era might seem forever beyond the reach of observation, ingenious physicists have devised ways to probe this ultimate frontier. The cosmic microwave background, mapped with exquisite precision by satellites like WMAP and Planck, preserves a snapshot of the universe when it was only 380,000 years old. But embedded within this ancient light might be subtle patterns that originated much earlier, during inflation or even in the pre-inflationary era. Gravitational waves, ripples in spacetime itself, offer another window into the earliest moments of cosmic history. The Laser Interferometer Gravitational Wave Observatory, LIGO, has already detected gravitational waves from colliding black holes and neutron stars. Future space-based detectors might be sensitive enough to detect primordial gravitational waves from the Big Bang itself, or from whatever preceded it. Different models of cosmic origins make different predictions about the spectrum and polarization of primordial gravitational waves. High-energy particle accelerators, like the Large Hadron Collider, probe the fundamental structure of matter and energy at scales approaching those present in the early universe. By recreating conditions similar to those that existed fractions of a second after the Big Bang, these experiments might reveal new physics that could illuminate earlier epochs. The discovery of the Higgs boson confirmed a key prediction of the standard model of particle physics, but it also raised new questions about the stability of the vacuum. We stand at the threshold of a golden age of cosmological discovery. New technologies and theoretical insights promise to revolutionize our understanding of cosmic origins over the coming decades. Space-based gravitational wave detectors, more powerful particle accelerators, and advanced computational tools will probe deeper into the mystery of what preceded our universe. The James Webb Space Telescope is already revealing surprising details about the earliest galaxies, showing us cosmic structures that formed sooner after the Big Bang than previously thought possible. Machine learning algorithms analyze the cosmic microwave background, search for gravitational wave signals, and explore the parameter spaces of theoretical models with unprecedented efficiency. Artificial intelligence is beginning to play a role in cosmological research, discovering patterns in data that human researchers might miss. The convergence of different fields, cosmology, particle physics, quantum information theory, and even neuroscience, is creating new perspectives on fundamental questions. The quest to understand what preceded our universe carries profound implications for how we understand our place in the cosmic order. If our universe emerged from nothing through quantum tunneling, what does that tell us about the nature of existence? If we inhabit one bubble among infinite others in an eternal multiverse, how does that affect our sense of uniqueness and purpose? Different scenarios for cosmic origins suggest different relationships between the observer and the observed, between mind and matter. The anthropic principle, whatever its scientific merit, raises philosophical questions about the relationship between physical law and conscious experience. If the constants of nature are fine-tuned for the existence of observers, does that suggest purpose in the cosmic design, or merely the tautological fact that we observe a universe capable of producing observers? Some find comfort in scenarios that make consciousness fundamental to reality, suggesting that mind rather than matter is the ground of being. The multiverse concept challenges traditional notions of uniqueness and significance. If every possible universe exists somewhere in an infinite ensemble, then our particular history, with all its suffering and joy, its struggles and achievements, is replicated countless times in identical copies. Some find this prospect liberating, others deeply troubling. Yet perhaps the most profound implication of modern cosmology is not any particular answer to the question of cosmic origins, but rather the very fact that we can pose such questions at all. We began this journey by asking what preceded our universe, a question that would have been meaningless to previous generations, but has become central to modern physics. Our exploration has taken us through exotic realms of theoretical speculation, eternal inflation and quantum tunneling, holographic principles and computational universes, cyclic cosmologies, and conscious creation. What unites these diverse scenarios is their shared recognition that the conventional notion of a temporal before breaks down at the cosmic beginning. The answers we have explored, if they deserve to be called answers, are as diverse as they are profound. Our universe might have tunneled into existence from nothing, emerged from the collision of higher dimensional brains, cycled through infinite rebirths, crystallized from quantum information, or computed itself into being through cosmic algorithms. Each possibility carries its own implications for the nature of existence and our place within it. The search for what preceded our universe continues to drive some of the most creative and ambitious research in modern science. New experiments probe deeper into the cosmic past, new theories extend our conceptual reach, new technologies expand our observational capabilities. We may be closer than ever to answers, or we may discover that the question itself needs to be reformulated in ways we cannot yet imagine. Perhaps the most remarkable aspect of this quest is not the exotic physics it uncovers, but the fact that it can be undertaken at all. In a universe that began as a hot, dense plasma devoid of structure, matter eventually organized itself into stars and planets, molecules and cells, brains and minds, capable of contemplating their own cosmic origins. The universe has become conscious of itself, asking questions about its own beginning. Whether our universe emerged from quantum nothingness or eternal inflation, from cyclic rebirths or conscious creation, the fact remains that it has produced beings capable of wonder, investigation, and understanding. In probing the mysteries of cosmic origins, we are participating in the universe's own process of self-discovery. The echoes of whatever preceded our Big Bang may be faint and difficult to detect, but they resonate through every atom in our bodies, every thought in our minds. Whatever preceded our universe, it gave birth to a cosmos capable of producing beings who could ask such questions and perhaps one day answer them. In the end, the search for what preceded our universe is also a search for what it means to exist at all. In the words of physicist Wheeler, we live in a participatory universe, where observer and observed, questioner and questioned, are inextricably intertwined.